All right, everyone. It's 1 o'clock. Welcome back. How did that homework set go? 6-2.
Not bad.
Okay. So I wanted to wrap up 6.2 with one more problem. And here it is in front of us. And this is similar to the problem that we finished with last time. If you recall, hold on, this is not it. Where is it? Oh, this one right here. So what we had here was a square root, and then we had a quadratic underneath that was not in the form that we needed in order to do a trig sub. So we had to complete the square first. And then once we got the completed square, then we went in, we did a little basic U sub, finally got it to the form where we could do a trig sub, did our trig integral, and then got our answer, went back to X. So this is a very similar problem because we have a square root, we have a quadratic, and the issue we have is that this is not in the form that we can do a trig sub right off the bat. So again, we're gonna have to complete the square. But there's something slightly different in this problem that I just want us to pay attention to. So let me write down the quadratic over here. I'm going to get myself ready to complete the square. And I'm going to start by writing it in descending order. So highest power of X down to a constant. Now, the first step for completing the square is to make sure that we have a 1 as a coefficient on the x squared. So here I have a -1, so I'm going to factor a -1 out of everything. Like that. And then I go about trying to do the completing of the square. So I take the number, the coefficient in front of x, I take half of it. So divided by 2, that gives me -2. That's one of my important numbers. Then I take that number -2 and I square it. And that gives me 4, and that's my other special number. And then this is where we'll realize the hidden 0. So we've got x squared minus 4x, and then here comes the hidden 0. The hidden 0 is going to be +4 minus 4. So I'm just taking that number and I'm adding it and subtracting it. And then we still have the -5 there. All right. Now, by design, the first 3 terms are guaranteed to factor to be a perfect square trinomial, which means that this becomes -1 parentheses, new set of parentheses, x, and then we use the number that we had here in the parentheses with the x, -2, and then squared. And then we have to put together the 2 constants that we have here, -4, -5, that's -9. And then close the parentheses. Okay, so there's where we are. Again, I'm going to go back to last class. I want us to look at this So on this one, when we completed the square, we pulled a 9 out in the beginning, right? And that 9 came here and it just kind of stayed there the whole time. And then at the very end, we had this. And then what we did is we realized that that 9 right there, that 9, we could split this into 2 roots, and we could take the 9 out as a 1/3. Is that clear to everyone? We did that step. We can't do that here because we have a -1 out front. You all see that? So you, even if you put it underneath the root, imagine we put this all underneath the root, which is where it's going to go. You cannot pull this -1 out of the root because you're trying to take the square root of -1. And the square root of a -1 is the imaginary number, or it's I, right? And we're not doing anything in here with I, nothing in this class.
Can we add that in the -9 or no?
What do you mean?
Can we add -1 and -9 and -9 together?
Yeah, well, we're going to distribute. That's what we're going to wind up doing, is distributing the negative in front here and to here. So what that's going to do is it's going to make it look like this. Like that, right? So negative in front of each of those. And the -9 becomes a +9. And then I'm going to change the order of this. Just going to write it in backwards like that. Okay? So that's an important step. You can't do anything with that -1. So you've got to push it back through everything. And so now our integral becomes integral square root of 9 minus the quantity x minus 2 squared dx. Are there any questions on that? You'll see how I dealt with that -1. Okay, now here we just, this is where I like to do just a basic u substitution. I'm trying to see that I have like 9, like square root of 9 minus u squared. That's the form I'm looking at. But I need to make a quick little u substitution. U is going to be dx minus 2. And then du is just dx, or 1 dx. And now my integral looks like it's ready for the trig sub. So I replace the x minus 2 with u. I replace dx with du. So here comes the trig sub. I replace u, because my variable is now u. I replace u with, let's see, a here for us is 3. And then what's the trig sub I use here?
A equals sine.
Sine theta, right? Then I know that the square root of 9 minus u squared automatically is going to become 3 cosine theta. And we know that when we take the derivative of this, du is going to become 3 cosine theta d theta. And then I can just rewrite the integral. So the square root part turns into 3 cosine theta. And then the du, don't forget the du, is 3 cosine theta d theta. 3 times 3 is 9, bring that out. Cosine times cosine is cosine squared. And how would we deal with this?
Half angle.
Half angle. So I'm going to have a half that comes out. And then I'm going to have 1 plus cosine 2 theta. That's me applying the half angle formula to cosine squared theta, bringing the 1/2 out. And then each of those I should be able to handle. The antiderivative of 1 is theta. The antiderivative of cosine 2 theta is 1/2 sine 2 theta plus c. And just like on that quiz problem, we have a sine of 2 theta, so we're going to have to use the double angle formula for sine in order to get that in terms of sine and cosine. But I will need my triangle. And my triangle is going to be based upon my original trig sub, which was this. Be careful because we have u here, not x, right? So I have u is equal to 3 sine theta And that means u over 3 is sine theta. And since sine is opposite over hypotenuse, I put u here, 3 here, and then I can solve for this side, 9 minus u squared. Okay, notice we are going to need to know what theta is. So to get theta, I just take this equation here and I take arc sine on both sides. When I take arc sine of the right side, I just get theta. So again, that's something that we've done before. I'm going to go ahead and kill this off. This right here, sine 2 theta, becomes 2 sine theta cosine theta. That's my double angle formula from pre-cal. And the 2's are gone. The 2.5, sorry, cancel out. So I think I'm ready for an answer here. 9/2, okay, theta, which is arc sine of u over 3. And then plus the 2.5 cancel. I have a sine theta here and I have a cosine theta here. Sine theta is u over 3. Cosine theta is root 9 minus u squared. So that's adjacent over hypotenuse plus c. And I guess the last thing to do would be to get everything back to x, because we're still in terms of u. So I had made a real quick u sub that u is x minus 2, right? Yeah, there it is, x minus 2. So I'm just going to replace all my u's with x minus 2, and we will be there.
Okay.
Put my 3's together, 3 times 3 is 9. There's my u, there's my square root of 9 minus u squared. Okay, so I mean, this was very much like the problem we did at the end of class last time, except for that -1. The -1 had to be pushed back through. Any questions?
I do have one question.
Yes.
I mean, two questions, but they aren't related to this problem. They're related to the homework problem 57 and 59. So I thought that I had a different way of solving it, but I just wanted to know if my way is like correct, because I'm not getting the same answer.
Okay, so let's look at 57. 57 was square root of 1 plus x squared over x dx. So what did you do?
So I started with the tangent, like I made x equal tangent theta.
Yep.
Then du was secant square theta d theta.
Dx is secant squared theta d theta.
And the square is secant theta.
Okay, good.
So I made the substitution secant theta over tan theta into secant square theta d theta.
Okay, I'm with you up to this point.
So at this point, I multiplied and made it secant cube theta.
Okay.
And I separated them. So I made secant theta 1 over cosine 3 theta into reciprocal of tangent, which made it a cotangent, cosine over sine theta.
So you did something like this. We're going to wind up with the same thing, hopefully. So when you flip that up,
I got 1 over cosine theta into 1 over sine theta. I mean cosine square theta. Yes.
like that.
Yes, and I just separated it 1 over sine theta, so I made it cosecant, and the 1 over cosine theta, I made it a secant square theta. And then I just, now I was stuck. So I was like, can I take the, separately, can I take their antiderivative separately?
Yeah, well, no, you can't remember because you have multiplication here, right? So you
Okay.
cannot do them individually.
So
Okay. I follow you up through that entire thing. I'm on board with you on this. Does anyone, so at this point you're kind of stuck, right?
Yes.
So does anyone have an approach that would work?
Aren't we supposed to write it down in terms of tangent minus 1 instead of secant squared?
You could do that. Do you want to
That
do
would-
that?
Wouldn't that be easier?
Well, maybe. Where do you want me? You're wanting me to replace the secant squared? Is that what you're saying?
Yeah, we can. Yeah, so yes, we can write basically the third step. Well, not there, way
Oh.
before.
Here?
Yeah, in terms of tangent.
You
and
could.
leave.
You could do that.
That would be a lot easier, I believe.
Well, let's see. So since we're kind of stuck on this, okay, I'm going to go back to this step, and what's being suggested is that we rewrite that secant squared as 1 plus tangent squared theta d theta.
Mhm.
Okay, I'm okay with that. Then what?
And then we use the double angle formula. No, I'm sorry,
We can multiply them together. That's what you did in your homework video.
no, because we think we can we write this?
We distribute the secant, and then we can take one off the tangent off of there. So it will be like secant theta minus secant theta tan theta.
So if we were to take this and distribute it here and here, the first one, we just get secant theta over tangent theta, then we get plus, and then when we distribute the second time, one of the tangents goes away, and we get secant theta, tangent theta. And the good news with this is now we can do them individually because we have a plus.
Okay.
The antiderivative of secant theta, tangent theta is just secant theta, right? The antiderivative of that. And then the other one, secant theta over tangent theta, you're probably going to have to do that one in terms of sine and cosine. So this is 1 over cosine theta over sine over cosine. And then when you flip this one up, you just get the cosines cancel. You get 1 over sine, which is cosecant theta. And that we can use our formula sheet for.
That's 14, or what number is that?
Don't know.
57.
Is
No,
it?
it's 15.
I meant the question, my bad.
Oh, yeah. Right here.
15,
Right here.
right?
Number 15, formula number 15. This is problem 57. Yeah, problem 57.
So basically, where I messed up was when I tried to do the secant square theta into secant, because there was a product, I cannot do them individually.
That's
But
right.
at that point, I was thinking if I could do integration by parts on it, which I could have done it, but then the problem would be very complex. Like,
Yeah.
so, okay, I understand that.
Yeah,
And my last,
It may have been able to go with integration by parts, but if you're doing a problem that requires trig sub and you find yourself like deep into it doing integration by parts, there's probably something easier, you know?
yeah. So my last question is problem 59.
Yeah. Yeah. Mm-hmm.
So here I made x 1 sine theta.
Okay, but you can't do that because this is not squared.
Yeah, so I treated the cosine here as cosine squared.
Yeah, you can't do that.
I cannot.
Cannot. Now, what you could do what you could do, and what you need to do, is you need to realize before you start the problem that this is 1 minus x squared squared.
Yes.
Okay, and if you do that, then you need to see that you have a basic u sub first.
Mm-hmm.
So if I let u be x squared, the derivative of that is 2x dx, which I practically have, right? X
Yeah.
dx. I just have to scale that by a half. And so what I can do is I can rewrite the problem. There's no trig sub here. This becomes square root of 1 minus x squared was u, but then I'm still squaring that. And then the yellow part turns into 1/2, so I'll put on the outside 1/2 du. Now you can do trig sub. You see that?
Yeah, I was able to understand it, but I thought maybe I could just, there was a basic logical error there when I was trying to treat the cosine to the square.
Yeah. So if you let x, like if you go back up to what you did, and you let x be equal to sine theta, right? 1 sine theta, that's what you were thinking?
Yes.
Then
I made the dx cosine square theta, cosine theta d theta.
that's okay. That's still okay. Here's where the problem is. What is the square root of 1 minus x to the 4th? See, because you have x to the 4th here. So if we just substitute sine theta in there, this becomes the square root of 1 minus sine to the 4th theta. And the problem is you can't use your Pythagorean identity. You can't use your Pythagorean identity on that to turn that into cosine. Well, if you think it's cosine of the 4th theta, it's not. Because then you're saying that the Pythagorean identity that we have, you're saying that that can be changed to this. Like we can make it 4th powers and it's still the same, which is not true.
So I didn't do this here. Instead, I did like 1 minus sine square theta and the sine squared. I did that. So
okay, so let's say you were to look at that as being 1 minus sine squared theta squared. This still can't turn into cosine. That's the problem. It still does not turn into, it's not equal to cosine squared theta or cosine to the 4th theta. None of those apply.
okay.
And I'll just remind everyone, just so, you know, if you're thinking about it, why does the Pythagorean identity, why does it only hold here? Why can't we change it to 4th power? Like if you think about that, here's the logic behind it. If we go back to the unit circle, okay, so this is the unit circle, meaning that the radius of this thing is 1. Then if you pick an arbitrary angle, okay, pick an angle theta, draw a right triangle, then we know that the x coordinate is cosine theta, and we know that the y coordinate is sine theta. Okay, that's something that you learn in pre-cal. If you're looking at the unit circle, then that's the relationship. We also know that this is 1, right? The hypotenuse is 1 because that's the radius of the circle. Then what we do is we just think about the Pythagorean theorem, a squared plus b squared is c squared, right? That's the good old Pythagorean. And for us, a is just cosine theta, and b is just sine theta, and c is just 1. And so what you get is the Pythagorean identity, cosine squared theta plus sine squared theta equals 1. The Pythagorean identity does not have 4s here. Okay, so you can't switch it to 4s. And that's why we can't switch our identities ever, right? It can only work when it's squareds. All right. Okay, we good? Anything else?
No, sir. Thank you.
Okay, no problem.
It's
Okay,
pretty
so
simple. I didn't know about all this stuff. I totally forgot.
what's that?
The unit circle and why everything's.
Yeah, we get so much information off of this right here. All right, so we are starting 6-3 today. We will only do half of it. And so the way 6.3 is going to work is this. Today, what we're going to do is we're going to take a look at integrals that we know how to do. All right, we already know how to do them. Now, we may not realize we know how to do them, but we do know how to do them. And then, so all this is preliminary stuff. All right, we're going to do a bunch of preliminary stuff. We're going to look at all these different integrals that we should be able to handle at this point. All right, then once we get through these 8 integrals, we will actually start the partial fraction decomposition and talk about the strategy. And even though all those notes look terrible, don't worry about it. All right, don't freak out. All right, it's going to be okay. So next class is when we'll actually start doing the problems that will require us putting everything together. All right, so we start though way back up here, the things that we should know walking in here right now. So let me move this over. I think that's good. All right, so first thing that we all need to understand is formula 17. We are going to use this a lot, all right? We've seen this formula before. In the beginning of class, I gave you this, and I said, please put stars next to this. The answer to this is arctangent of x plus c. Do I remember me giving you that? Mm-hmm. Okay, this formula 17 is basically that formula with one change. Instead of requiring that that be a 1, that can be any number. All right, so over here in the formula, the u is the variable, so u is like the x here, and then we have like an a squared, like we've had in that trig sub that we've been doing. So let me give you a specific example. If we had the integral 1 over, let's say 9 plus x squared dx, we wouldn't have to work that out. Okay, we don't need to work that out. We need to know that that's formula 17. We need to know that a for us here is what? What would this tell us a is?
3.
3. And so we just write the formula down. 1 over a arctangent of u over a, but our variable is x. So I'm going to put x over 3 plus c. And we're done. All right, we're done. No work. Let's do another one. Okay, we need to be able to look at that and be like, oh, yeah, formula 17. A for us this time is what?
1.
No.
Square root of 3.
Square root of 3. So what you always have to remember is that whatever this number is, that's a squared. So if you want a, just take the square root of it. So it'll always be the square root of that number. So the square root of 3, since it's not a perfect square, that means a is just root 3, and that's what it is. So the antiderivative would be 1 over a arctangent of x over a plus c. And that's it. We're done. Is that okay with me writing the answer like that and leaving it like that?
Yeah, I was going to ask you, do you want us to rationalize the 1 over square root 3?
So let's take a vote. How many of you think that we need to rationalize that? Like you can't leave a square root in the denominator, like I just did with the root 3. Let's take a poll. How many of you think that you have to change that? Yes or no? Rationalize. Okay. So the results here, we're about 50%, 50-50. So let me ask someone to volunteer. Someone who said yes, do you want to explain why we have to rationalize it?
I always been taught that you don't have, like, your answer can't have a square root, like, in the denominator.
Okay.
So that's why I picked yes.
Okay. And how about someone who's saying no?
Oh, I said no just because I feel like in certain instances you don't have to.
Okay.
I guess in
So-
examples like this, doesn't matter, but once stuff gets more complicated, you can easily make mistakes, and then you will have I guess, the result wrong.
Okay. So when I was a student, and we're actually going to take a little bit of time to talk about this, even though we don't have time. Are y'all still there? Why is my OneNote? Uh-oh. Something is happening. It must really want us to rationalize it because it's not responding. Did y'all see that?
Mm-hmm.
That's weird. Okay, I'm just going to try and close it. This hasn't happened in a while. Right.
Control Shift Escape.
Yeah. I can't do that. This keyboard is messed up. Hold on. Shit. I'm going to end it. All right. I'm not sure what happened with OneNote there, but we'll try and reopen it. In the meantime, y'all doing okay? Come on,
Yeah.
man.
So from your point of view, is it okay if we leave the square root there?
Yes, it's okay, but we should talk about why. And we may not be able to talk about why. At least, I have no idea what's going on here. It's weird. My computer seems to be responding, but OneNote isn't. Anyone have any suggestions here?
You could restart.
Yeah, let me get in.
Open your task manager.
I'm trying to right now, and all my screens went black. Hold on. I don't know if y'all can still. If we get disconnected, I'll reopen the meeting.
Then yeah, you might have to.
Wow. What the hell?
Because if your task manager is not coming up, something really wrong is happening.
Yeah.
We could just call
I've
it a
got all
semester
black
and end the
screens.
days.
Wow. Okay, I'm gonna just reboot. All right. So I don't know what's gonna happen to you all, but I'll be back in a minute.
Class is canceled, everybody.
We're not that lucky.
There it is, King Cameron.
I don't know why it made me host.
Now you can dismiss us.
Now I can stop him from getting in.
Okay, can y'all hear me?
Mm-hmm.
Okay. See my screen?
Yep.
Okay. Sorry, guess we're still having class. All right, so back to this. So here, I'm going to try and make this quick because we've already lost several minutes here. Let's just take a look at this expression, 1 over the square root of 2 versus rationalizing it. So if we rationalize it, we have to take this and multiply it by root 2 over root 2. And the reason we do that is so that on the bottom, when we multiply these together, we get a nice number and the root goes on top instead of the bottom. So right now, if we were to get on a calculator and we were to type this into your calculator, do 1 divided by square root of 2, you should get, someone do that. I think it's 0.70.
0.7010678812.
So both of these give you the same answer, right? Whichever one you type in, they're the same answer. So people are told, including myself, when I was a student, I was told you can never leave it like this. You always have to turn it into this. And I'm like, well, why? I mean, it's the same answer, right? So why does it have to look like the one in green? Well, there's some history behind it. And once I tell you the history, you're going to agree with me that the yellow is just fine. You can leave it like that. So think about the day back in the past, days when there were no computers or calculators, all right? And math, you know, you're taking a math class and you had to figure out like what this was. Well, you had to have certain things memorized. Okay, so students back in the day, they used to have to know that square root of 2 is approximately 1.414. They had to know that pi was approximately 3.1415. They had to know that E was approximately 2.718. And there was a bunch of numbers that people in math classes just had to know, all right? Because there was no calculator they could plug it into. In fact, they used to have competitions on who could memorize these numbers the furthest out. So like there would be a competition, who could memorize pi to
We're
the
missing a 92, no? On that one?
What's
Is it
that?
92 after the 15?
I don't know. I don't know. I'm not part of that generation. But I mean, I have a colleague of mine who's in his 60s who can still recite pi out at least 60 digits out of memory. And he said he had it memorized out about 120 to 130 digits at one time. And I think the world record is like 16,000 digits. But anyway, so imagine you're trying to do this math problem, right? And all you have are these numbers memorized. Think about what math would be required to simplify this 1 over root 2. You would have to go to old school long division. You'd put 1 in here, and out here you would do 1.414. And then you'd have to try and start figuring out, like, what do you multiply this by to get 1? Right? And that's a difficult question. But compare that to what the question would become if you do this one. So you rationalize it first. Well, what goes in the division box this time?
2.
The root 2, right? So 1.414 goes here, and outside goes the 2. And what's easier to do? The one on the right, right? Because you'd say, okay, how many times does 2 go into 1? Oh, it doesn't, so I put a decimal point. How many times does 2 go into 14? Oh, 7 times. Okay, it's 14. You bring down, do you see what I'm doing here?
Mm-hmm.
And then you could figure out that that's 0.707. So it all comes down to, historically, we didn't want to leave radicals in the denominator because we didn't want to have to do that computation by hand. The days have changed, right? We have calculators. Taking this on our calculator is just as easy or hard as doing the other one. So it makes no difference. So there's no rule that says you have to do it. And if your teacher tells you you have to, then they're just reciting what they were told, all right? There's no reason for it though. So I'm leaving my answer like this. All right, now, that's the first thing. I need to open up my Mathematica again, bring up my notes. Oh, there it is. All right, so we have that first formula, right? Now, what else can we handle? So let's look at this next problem. We want to make sure that we're all comfortable with an integral that involves a constant on top, constant being any number other than 0, over a linear expression. We should all be able to do that. For example, if we have 2 over x minus 4 dx, without doing any work at all, really, we should understand that this really looks like 2 times 1 over x minus 4 dx, and that we could visualize that this entire denominator, because it's linear, is like, it would be like a quick u substitution, right? And we would get something like 1 over u. And we know that the antiderivative of 1 over u is natural log of u. You all agree? So this should just become 2 natural log of u, but the u is actually x minus 4 plus c. Right? No work. That should just be automatic. I'll do another one. Here's number 2. We have a constant on top. We have a linear expression on the bottom. I know this is going to be natural log, right? In fact, I know the answer. This is going to be natural log of the 4 minus 5x, like that, plus c. But this time, I'm missing something. What am I missing? Think about what the derivative of this would be.
The constant minus -5.
See this -5, right? Wouldn't that pop out in the chain rule? If you took the derivative of this, you get 1 over this, and then you get times the derivative of what's inside, you'd have a -5 out there, wouldn't you? You don't want that -5. So I'm going to have to scale this by -1/5. It's kind of like we did with the cosine and the sine. Remember we were learning that if you had a linear expression inside cosine or sine, you'd have to scale by 1 over a. Same sort of thing here. Let me see if you're really getting this.
But wouldn't that be considered also part of the constant, the 1/5?
With this constant?
Yeah.
No, because this is addition and this is multiplication. We're scaling this entire thing by a number as opposed to adding something to it. Multiplying by a 5th is not the same as adding a 5th.
Okay.
What if we had this? This is kind of like a general formula here. We have a constant over a linear expression in x.
So it'll be 1 over a.
Yeah, 1 over
ln,
ln
ax plus b plus c.
ax plus b plus c. There we go. That would be like a general formula. Now, I'm not wanting you to try and memorize that. I want you to just think through it, right? I'll give you one more example. Trying to confuse you now. Okay, the 5 on top is going to come for the ride. So it's like I pulled the 5 out of the integral. Everything else you have there on the bottom is a linear expression. Remember, e and pi are both numbers.
Is it going to be 5 over pi?
That should be 5.
What's the number in front of x?
5 natural log of e, right? And then the whole thing, the whole bottom piece.
Let me put the natural log. The natural log is just going to have everything that was in there. Okay. The question is, what am I going to scale by?
1
1
over
over negative e.
1 over negative e. Because the number in front of x is negative e. So a is negative e. You could leave it like that, but I'm just going to write it 5 over e natural log pi minus e times x plus c. Okay, so everyone in here should be able to handle any integral that has a number on top of a linear expression. Agreed? Yes?
Yes.
Okay, let's see what else we can handle. we should also be able to handle anytime we have a constant over a repeated linear factor. We should be able to handle that. As an example, 1 over 2x plus 1 squared dx. So the thing that makes this repeated is the fact that it's squared. So we have 2x plus 1, that's linear, right? But then we are repeating it, which means that we are squaring it, or that could be a cubed or a 5th power or a 10th power, or it could even be a square root, cube root, doesn't matter what the power is, as long as it's a linear expression to a power. And it's the same idea. We imagine that this could be a u, right? And so at the end of this, if we were to make a basic u substitution, this would turn out to be u to the negative 2 du. Now we'd have to scale. In this problem, what would we have to scale by?
1 over 2?
1 over 2, right? We'd have to account for that 2 in front of the x. That's going to be with us throughout all these types of problems. We know that we're going to need a 1 over 2. But this is mainly what the integral is going to be. And do we know what the antiderivative of that is? It's not natural log this time, right? It's not
It's
natural log.
1 over
Is it
here.
u, 1 over u?
Yeah, negative 1 over u is the antiderivative of that. So I'm not look at what I'm putting here in blue is not like work. Okay, it's not like I'm expecting, it's not like I'm showing you how to do this problem. I'm showing you what you're supposed to be thinking, okay? This is supposed to be happening like almost mentally. So I'm gonna go to the answer now, all right? So I know the antiderivative of that should be the 1/2 I have to scale by because of the 2 in front of the x. Then I'm gonna have negative u, which is 2x plus 1, raised to negative 1 plus c. I'm going to give you another one, see if we can get it quickly. I could rewrite that, okay? If you're not happy with the way that looks, you could put like negative 1 over 2, then 2x plus 1 plus c. If you want to drop that 2x plus 1 down, you can. All right, let's see if we can handle this one. I'm going to give you a constant on top. I'm going to give you a linear expression on the bottom. And I'm going to do it repeated. Okay, so we know that the 5 is going to come out, right? The 5 is going to be here. What am I going to have to scale by?
1 over 4.
1 over 4, because the coefficient on x is 4. And then at the end of the day, this really looks like what integral to us?
U to the power 8.
U
1
to the
over u.
power negative 7, right? Because that's going to be like
Oh.
1 over u to the 7th power. Y'all following me or no?
Mhm.
Yes.
You gotta let me know if you're not. I can go into more detail. The antiderivative of u to the negative 7 would be what?
1 over negative 6 over u to the 6, negative 6.
1 over 6 u to the negative 6, and then we would have plus c, right? That's kind of what we would have. But what's u for us?
4x minus 3.
Or x minus 3 is what goes here. So let me try and clean all that up. That's going to be negative 5 over 24, and then u, which was 4x minus 3, to the negative 6 plus c. One more?
Sure.
Okay. How about this? Negative 3 over the 4th root of 2x. Let me make it more complicated. 3 minus 5x dx. Okay, so what you have to pay attention to here is the fact that this is really like negative 3 outside, and then we have a linear expression to the 1/4 power dx. The key to this whole thing is the fact that this is linear. And because it's linear, we can always make that u. And then du will always just be a number, and we can scale that number out. And so all of these are always going to wind up being a u to a power. Now, there's a special case where it's to the first power, 1/u, and that's natural log. But if it's any other power, then we can use the power rule. So I'm ready for the answer here. We're going to have -3. I'm going to have to scale by what number?
-1/5.
-1/5, okay. And then
It'll
this is
be
really like u to the,
-1/4,
yeah, it's really like a u to the -1/4.
which would be
Which when you take
3/4.
Yeah, it should be 3/4. So we should have a 4/3 in front. And then the u, which is 3 minus 5x to the 3/4 plus c. Now's the time if you have a question.
So I mean, how come we didn't do all of this like beforehand?
Well, what do you mean? There's nothing that I've done well,
So I mean, like when we were doing the u substitution, like this is like straight up. Don't even have to do a u substitution and all that.
well, this is a special case. This is right now. We can only handle a constant over a linear expression. That linear expression raised to a power, right? It's a very
Okay.
special case. It's a very narrow field. This, if I just showed you this, this would not encompass all of what U substitution is, right? There's a lot of other problems that aren't like this.
Yeah.
The whole point of this is just to show that, look, like, yes, we could go through the U substitution, right? We could do that for each of these problems, but it's going to take us too long, right? So we want to be able to do these mentally more or faster. All right, you ready for the next type? Well, this is, okay, so this one I hadn't done. Why don't you take a second to do that one? Yeah, I'm gonna give you, let me see what the next one is. Yeah, we're not ready for that one yet. Okay, just do that one real quick. Take it all the way to the answer. I'll be right back. I'm gonna go, it's getting hot in here. I'm gonna go turn on the air conditioner. All right, so we don't have to scale, right? We don't have to scale this one because there's a 1 in front of x. So this really looks like a u to the third on the bottom, which is really like a u to the -3.
Mm-hmm.
And the antiderivative of that would be -1/2 u to the -2. So -1/2 times x minus 5 to the second plus c.
Yeah.
Okay.
Can we keep the -5 with the -2 power on top?
Yeah.
Okay.
You mean just replace that u right there with x minus 5?
Yeah,
Yeah,
that's
you can
right.
do that. Yeah, that'd still be correct.
Okay.
Okay, so as it sits right now, any integral that you ever see that has a number on top and a linear expression in the bottom, you should be able to handle, right? Whether that linear expression is by itself which would turn into a natural log, or that linear expression is raised to a power. You should be able to deal with it. All right, let's see what else we can handle. Okay, here's where things get different. They change. If we have a constant on top, and on the bottom, no longer linear, we have a quadratic with no x term. All right. If we have a quadratic with no x term, we should be able to handle it. First example here, can somebody tell me how you'd handle this one?
I thought it was going to be x minus 3 plus x minus 3, but I don't think that is.
No, it's, I think,
Not subtraction between those, so.
Isn't it 1 over a, I think it's, or, yeah, 1 over 3 arctangent of x over 3 plus c?
See, so this is formula 17, isn't it? This is actually what I started today with, or started this topic with. Remember, we've got this, right? We've got this formula. So if we ever see a quadratic where we are missing the x term in the middle, we should be able to deal with it, right? From what it looks like right now. Now, how about this? Let me change the problem. What if we have this? So this is what Abe was talking about, I think.
Yeah.
X squared minus 9 is a difference of squares, right? We cannot use formula 17 for this. Formula 17 has a plus sign in there, and you can't just use the formula whenever you want, right? So this integral, we cannot use formula 17. So what we would have to do is something, well, what we could do is something like this. This is what Abe was suggesting earlier. And that, at this point right here, we're stuck, okay? And that's what next class is going to be about, how to deal with that. So right now, we are going to leave this as an open question, all right? And leave that as an open question. But if we have a quadratic on the bottom and we're missing the x term, and if you want, you can add to this note over here. You're missing the x term, and it's a plus there. Plus in between, then we've got formula 17, all right? If it's a minus, we'll be able to factor and do something later. Just right now, we can't. Cameron, is that all right?
When you say no x term, you mean like no x coefficient?
Yeah, we have an x squared, right, term. We have a constant term, but we're missing an x to the first power.
Yeah.
The middle number.
Yeah, the middle x is missing.
Oh, okay. Okay, that's what you mean. Okay, yeah. I
I
thought
mean,
you
we do have an
No.
x in there, but it's not an x by itself. It's x squared.
Okay.
can
Okay. so
we just do a simple substitution here?
It wouldn't work. Du is not present anywhere. Right?
Oh.
If you let u
And
be
we
like
cannot
x
split
squared.
it either.
Oh, yes.
Yeah, you cannot split this. You cannot split this. Come on, man. You cannot split this here into two fractions and do them individually because you'll have a multiplication between them, not an addition.
And not even integration by parts?
No.
Don't think it's going to work. Don't worry. Next class, we'll handle it.
No, I'm just curious.
So again, recap. Constant over linear to any power we got. Constant over a quadratic where we're missing the x term and there's a plus in the middle, we got it. Formula 17. Okay, what else can we handle? A constant over an irreducible quadratic. I'm not going to write that down again. I'm just going to write the problem down. What do I mean by irreducible quadratic? Does anyone know what I mean by irreducible?
Can't factor it?
Can't factor it. That's exactly. So if you want to replace irreducible with the word can't factor, so do you all agree we have a constant on top? On the bottom, we have a quadratic that cannot factor. Like there's no way to break up that quadratic nicely into two things that are being multiplied together, like x plus some number, x minus a number, or anything like that. This is a no-go, right? So how do we deal with this? Like I said, you actually know how to do it, you just may not know that you know. Does anyone have a guess as to what we could do?
Quadratic formula?
That's if we were trying to solve a quadratic equation. We would
Trig
use
sub. Completing the
trig
square.
sub, is that what I heard? Or trig sub, what did I hear?
I said trig sub.
Okay, so if we do trig sub, we're going to need to have like a square root of something, and it's got to look like, you know, x squared minus a squared, or a squared minus x squared, something like that. All right.
What about completing the square?
Complete the square. That's it. We'll complete the square first. Let's complete the square. I'm going to go fast because you have all had time now to master completing the square. I say that with a grin. So what I did is I took the number in front of x, which was 2. I took half of it, which was 1. I squared it, which is 1. I'm going to add and subtract it. So I added and subtracted a 1. That means my first 3 terms will guarantee factor to be x plus 1 squared. Then I still have a plus 16 out here. Does that make sense, everyone? Okay, now take a look at the integral.
Now you can do it separately?
Not separately. Not separately. Look, squint your eyes. You have to squint your eyes a little bit to see this. Isn't that linear expression right there kind of like a u?
Yeah.
So isn't this like a 1 over u squared plus a squared?
Yeah.
Yeah. So how do we handle that?
So it'll be 1 over
A
1 over 8.
4, right? Arctangent of u over a. But what's u for us?
X plus 1.
X plus 1 over 4
4.
plus c. So it actually turns out that formula 17 would work for this also, wouldn't it?
Mhm.
Formula 17 would work. We have to complete the square first, then we have to realize that what's in here is kind of like a u, and so it basically looks like a 1 over u squared plus a squared, so we go to the formula 17. That will work for irreducible quadratics on the bottom and a constant on top. Now, I want you to not get too far ahead of yourself. What if we had this problem? No, hold on, no, I'm not ready for that. Not ready for that, sorry. All right, so shall we recap again? I'm gonna recap every time. Constant over linear, we're good. Constant over linear to any power, we're good. Constant over a quadratic that is missing the x term and has a plus, we're good. Constant over a non-factorable quadratic, we should be able to complete the square and use formula 17, we're good. How about a linear expression over a quadratic expression? A linear over a quadratic. Linear over a quadratic. All right.
So I think we'll still do the complete the square.
Okay, completing the square might lead us somewhere, but because of time, I'm just going to take you through this, okay? I want you to put a star next to this because let me kind of explain to you the path I'm about to go I was taught how to do a problem like this a certain way, okay? Certain way. Usually most books follow that same way. Most tutors that you'll ever talk to will follow that same way. The way I do it is very different, right? And I can't tell you why I do it this way other than I really like it. And I think it's better for your brain to think about it this way. So we'll see what you think about it. But I'll tell you right now, up to this point, every problem we've done has been somewhat straightforward. I mean, there hasn't been a whole lot of stuff we've had to do. For this problem, put your seatbelts on. Here we go, all right? So think about this. If someone ever hands you a quadratic function and you take the derivative of it, what can you tell me about the derivative? What type of function would that be? If you start with
Linear.
the quadratic and you take the derivative.
Linear?
Linear. Does everyone agree with that? You start quadratic, take the derivative, and you've got linear. Well, if we're looking at an expression where the denominator is quadratic and the numerator is linear, it's almost like perfectly set up for me to let u be the entire denominator. Because if u is the entire denominator, everything down there, the derivative of that quadratic should be linear. And maybe I'm going to get lucky. Maybe the numerator is the derivative of the bottom. Let's see. So I'm going to make a u substitution that u is the entire denominator, everything, right? I'm not completing the square. I'm not completing the square because the numerator is not a constant, right? If the numerator were a constant, I'd be completing the square. But because it's linear, I'm making a u substitution. Now I'm going to take the derivative. Du is 8x minus 4. Notice I put that in parentheses, dx. Now, do we have 8x minus 4 dx up top?
We can divide by 1/4.
Okay, so if I divide by 1/4, won't I have 2x minus 1? Right? It'll be a little bit off, won't it?
Yes.
So what I need everyone to see is this right now. That's really what we have, right? I just peeled that numerator off to the side. Life would be beautiful if this and this matched, right? If they matched, then wouldn't that just be du? And then the rest of the integral would just be 1/u, and we just have 1/u du, right?
Mm-hmm.
Wouldn't that be great?
Yes.
We don't have that though, so life ain't great, okay? But I'm going to force it to happen, okay? I'm going to force it to happen. And this is the part that, like I said, if you go to a tutor, they're going to take you through this like procedural way of doing the problem, and there's not a lot of like really deep thinking about it, but I want you to think deeply about this. What I'm going to try and do now is I'm going to see that part in green. That's the part I wish was there, right? I wish I had that. So I'm going to force this part in blue to be the part in green. And the first thing I'm going to do is realize that there's an 8 in front of the x. And that means I need an 8 in front of that x. And the only way to get an 8 there is to multiply by 8, right?
Yes.
But you can't just multiply something by 8 because that changes the problem. So I'm going to be super clever, and I'm going to multiply on the outside of the integral by 8/8 because that's a 1, isn't it?
Yes.
Okay. So if I multiply by 8/8, I'm going to leave the 8 on the denominator there. I'm going to pass this 8 through, and it's going to hit that parenthesis and pass through the parenthesis. So now I have this. You know what? I don't normally do that in my work, so I'm going to do this. I'm going to put it back up here. I'm just going to slide it back up. Is that all right that I just slid that blue part back on top?
Yep.
Okay. Now, we're getting close, right? We're getting close. We have now magically made an 8x appear. I want there to be a -4, right? but I have a minus 8. So watch what I do. 1/8. Okay, I have an 8x. What would I want there to be?
-4.
Okay, here it is. Here's -4. But I can't just do -4, right? I have to, if I'm going to subtract 4 just arbitrarily, I also have to add it. So guess what that is? It's a hidden 0, isn't it?
Yes.
Okay, now what was still up there? What was still there? I kind of threw that in there, but still sitting next to that is -8, isn't it?
Right.
All over 4x squared minus 4x plus 3 dx. Any questions?
No.
Okay, now I'm going to put those two together. Of course, 4 minus 8 is -4. And then what I'm going to do is I'm going to split this integral right there. So I'm going to do this. I'm going to do 1/8 integral. Okay, what's the first numerator going to be? Because I'm going to split this into 2 integrals. What's the first numerator going to be? 8x minus 4, right? Over the denominator. And then I'm going to say plus 1/8 integral. And now the other numerator part, which was -4, over 4x squared minus 4x plus 3 dx. Okay, now is a good time for you to ask me a question. Like how did you do that? Or why did you do that? Or where did that go? Or
So why would we take a -4 out?
we will. We will. I just wanted to
So-
stress that what we did is we made 2 integrals. One integral was this one over the denominator. The other integral was all of that over the denominator. So I split it up into 2. But I will, that -4 will come out on the next step. Any other questions?
So in the,
Somebody tell
so in
me
the
why-
second integral,
Yeah.
where would the du be?
Oh, okay. Okay. So yeah, I know where you're going, Minato. So let's take one step back, Minato. Why do you think I did this? What can you tell me about the first integral? How would you go about the first integral now?
The first integral, I would replace 8x minus 4 dx with du.
Is the
Yeah.
integral of du over u, and the
Yeah,
other
so
one, it's
we already
linear.
know. We already know, right? Like this integral over here is going to be like so nice because we know that if we let u be the denominator, the derivative of it is up top, right? It's going to be a basic u sub. We're happy. We move on, right? Life is great.
Mhm.
Understand? The other integral, I'm not going to do u substitution on. But what type of integral is it?
It's 1 over
Constant over
1 over n.
quadratic.
Constant over quadratic. That's
Right.
irreducible. And what do you do for that?
Complete the square. You can complete the square and then,
There you go.
oh, okay. That makes sense.
Yeah, so I've created 2 integrals. One's going to be easy. The other one's going to be like the problem number 6 here, right? That I showed in the notes. It's going to be, okay, well, life isn't that great. We got to complete the square. Oh, well, right? All right. I told you this problem was going to be like, buckle up, because it's going to be a long problem. We still have a lot to do. All right. Can we take care of this blue integral first? I'm just going to write down what we're doing. We're doing u is the whole bottom. The derivative of that is everything we see there, right? We're super happy about that. And so that integral becomes 1/8 integral 1 over u du. And we know that that's just natural log. So we know the answer to the first part is natural log of 4x squared minus 4x plus 3. Bam. So that's the answer to the first integral. Let's work the second one. Let's pull the -4 out. -4 over 8 is -1/2. Integral 1 over 4x squared minus 4x plus 3 dx. Need a little more room here. All right, so now we have to complete the square, right? Because we have a constant over an irreducible quadratic. How do we know that's irreducible? How do I know that doesn't factor? I'd have to check, right? I'd actually have to see that it factors. And so this goes back to college algebra. What you're doing is you're saying, you're multiplying those two numbers together. You're saying, okay, that's 12. And you're taking the number in the middle, -4. And you're trying to come up with two numbers that multiply to be 12, but add up to be -4. You have to think of two numbers that multiply to be this and add to be this. And you'll sit there all day, you're not going to find them. Okay? So it's irreducible.
I mean, I think at the point that it wasn't reducible earlier on, would have hugely impacted how we would have solved this problem.
Wait, can you restate that?
Like if it was reducible, I think it would have impacted how we could have solved the problem.
That's right. And we'll see that next class. Next class, we'll deal with a problem where we might have a linear expression on top and a reducible or factorable quadratic, and that technique will be slightly different. But we're dealing just with irreducibles right now. Okay, let's complete the square. We are going to complete the square. And we're going to complete the square on the entire quadratic here. All right, so we take, the coefficient has to be a 1, right? So 4 out first. Do not forget, when you pull a 4 off the 3, it becomes a 3/4. Don't forget that. 4 comes out of the 4x squared, 4 comes out of the 4x, but the 4 out of the 3 turns it into a fraction. We identify the number in front of x, -1. We divide it by 2, and that's just -1/2. Then we take that -1/2 and we square it, which gives us 1/4. That's our hidden 0. We're going to add and subtract a 4th. So I have 4 times x squared minus x. Here comes the 0.
Why is this completing the square method different from what we learned in college algebra?
Because it's very common in college algebra to teach, for teachers to use the fact that you have an equation. See, when you're doing completing the square in college algebra, you're dealing with equations, quadratic equations. So you have 0 on the other side, so you can always work with both sides of the equation. Unfortunately, we don't have an equation, we just have an expression. So we are forced to do it this way. And if I didn't say this last time, I'll say it again. I think some of the problem with that is that normally when you take college algebra, and I don't want to, because I'm on the record here, I'm being recorded, I don't want this to come across bad, but I think professors will be honest with themselves when they say that sometimes your college algebra professor never teaches calculus, like they don't teach calculus. And so they may teach it because they don't like it. They may teach it because they're not comfortable with it. Okay, just because you have a master's degree in math doesn't mean that you can go teach calculus, right? Like you may not be comfortable with that. So I think what happens is you have a large percentage of math teachers that teach college algebra that don't even realize that later on completing the square is required and that you don't have equations, you have expressions. Because I think if they knew that, then they would never teach it the way they teach it with this. Like they would never do that because they realize that later on you're gonna have to relearn it, kind of. Does that make sense? It's not a bad thing. It's like this. When you're learning the quadratic equation, right? When you're learning the quadratic equation, ax squared plus bx plus c equals 0, right? You learn that the solutions to that are -b plus or minus the square root, b squared minus 4ac, all divided by 2a, right? You get that formula. Someone at some point in your life taught you that formula, right? Okay, do you think that your teacher that taught you this formula actually knows how to generate that formula? Maybe, maybe not, right? Maybe, maybe not. But if you learn that in like maybe middle school or high school, there is a strong chance that your teacher probably couldn't show you where that formula came from, right? So, but does that stop them from being able to
Use it now.
teach it to you? No, right? So the completing the square, the way it's presented in college algebra, is usually the way that you've seen it, equal to 0, right? The problem with that is it doesn't think about the future, right? Doesn't foresee what's coming down the road. So I don't know. I'm sorry. I could keep going on about this. We're not going to though. All right. We're completing the square. Hidden 0. There it is. There's my hidden 0. The first 3 terms will come together. They will become x minus a half. That's that first magic number we have there, squared. And then I have to put these 2 together. And oh, good for us, right? What is that, a half? Any questions there? All right. Now I'm ready to replace everything under that 1 with that. And that 4, I'm going to bring it out of the integral on the bottom. Okay, can somebody tell me how to deal with that? Squint your eyes.
Let u be x minus 1/2.
And then that
Formula
looks a lot
17?
like formula 17, good, right? That looks a lot like 1 over u squared plus a squared. Now, be real careful here. What would a be for us then?
1/4.
1/4.
Careful.
Square root of 1/2.
The square root of 1/2,
Mm.
right? It's the square root of that number. So you take the square root of the top, you take the square root of the bottom. So a is 1 over root 2. Negative 1/8 comes down. Now formula 17. Formula 17 says 1 over a arctangent of u, what's u? X minus a half over a 1 over root 2 plus c. Bring that answer down here, and that's your answer. So I know that some of you may get some help from friends or a tutor or something like that. And I know that if you see it the other way, you might be like mad at me for showing it to you this way and be like, you know, it's just easier the other way. And I get it. But like I said, this to me is, there's just something that is, something about this making this thing appear up here like this, like forcing this 8x minus 4 to happen. I think that is a better thing for you than just learning to do something mechanically without thinking. Like that requires some thought. And I think an engineer, a computer scientist, that's the way you're going to have to think later. You're just going to have to be thinking kind of outside the box a little bit. So, okay. Let's, yeah, that's kind of nasty, huh? How about this one? How much time do I have? I have enough time, yes. Let's see if we can handle this one. All right, so the one we just did was a linear expression over an irreducible quadratic, right? This next one is a linear expression over repeated irreducible quadratic. So this part in yellow is the irreducible quadratic. X squared plus 1 cannot be factored, right? X squared minus 1 could be factored, but x squared plus 1 can't be factored. And it's repeated. It's repeated, right? Which means that it's squared or cubed or fourth power, something like that. And so the question becomes, how do we deal with this?
Expanded?
Oh, like multiply the whole bottom out? We could do that.
Yeah.
We could do that because it's squared, right? It would be easy for us to do it. But what if that was like to the 5th power? Like you probably wouldn't want to deal with that, would you?
No, but here, since it's 2, so I would go ahead and do it and like try to solve it the way we did it in a previous example.
But if you expanded that, wouldn't you have x to the 4th? Like the first time you multiplied that out?
Yes.
You sub the bottom.
So let's see, x to the 4th.
Plus 2x squared.
Plus 2x squared plus 1. And see, the problem with that is if we try and do what we did previously in the previous problem, if we let this be u, the derivative of that is 4x cubed, and I don't have 4x cubed up top, do I? Right?
Now, cannot I just do like, I make x plus 1 over this equation and do a completing the square?
Completing the square where?
Like at the bottom when I expand the whole equation?
You don't need to complete the square if the denominator is okay, x squared plus 1 is already completed. Like that's already in the form of a completed square, because a completed square always looks like this. It's one or the other. That's what a completed square looks like. It's something squared plus something squared or something squared minus something squared. So we already have a completed square in x squared plus 1. Now I heard someone say something, a u substitution of x squared plus 1.
Yeah.
Okay, let's go for that. Let's just see what happens. If we let u be equal to x squared plus 1, what's the derivative of that?
2x
2x dx.
scale.
Right? So this is kind of like the same exact thing that we did in the previous problem. We had a linear over an irreducible quadratic. We said, hey, let's just let u be the part here, the quadratic part, right? Let's let u be the quadratic part. Here's what we'd love to see in the numerator. Oh, we don't have it. Oh, let's make it happen. And then everything worked out after that. Same sort of principle here. What's the irreducible quadratic part? Okay, let's make that u. What's the derivative of that? 2x. Do we have 2x? No, we have x plus 1. Could we make it a 2x?
Scaled it.
Scale it, right? We'd have to do it on the outside, though. We would have to do 2 on top, 2 on the bottom. Now that plus 1 is going to be an issue. Do y'all agree with that? That plus 1 is going to be an issue? But let's still do it. Okay, I'm going to force the 2 through the top. One half still out here. 2x plus 2 on top. Here, x squared plus 1 squared dx. Now I wanted just 2x, didn't I? Like if that top was just 2x, I'd be okay. You'd be okay. We'd all be happy or no? If it was? Okay. Well, it is kind of, if we split this into 2 integrals now. So let's go 1/2, and then the first integral is just 2x over x squared plus 1 squared dx. And then the other integral is plus 1/2 integral 2 over x squared plus 1 squared dx. All right. How do y'all feel about that? Do you see this first integral can be done with that u substitution?
The easy part, but now we can't complete the square.
That's the easy part, right? Because that's really going to just turn into an integral. It looks like this. Integral, we'll have a 1/2 out there. It'll turn into like 1 over u squared du. And then we can use our power rule on that. You'll follow?
Mm-hmm.
The second integral, the one in red here, that's,
So we cannot treat this one as case one where we had a linear, a constant over just a linear function because of the x squared. This is quadratic.
you mean this one here in red?
Yes.
Yeah, we know how to deal with a linear over a repeated linear, a constant over a repeated linear, but this is a constant over a repeated quadratic.
But can't we do a 10 here, the arctangent?
Can you? Well, the thing is on the arctangent formula, you can't have that squared there. Like if that squared wasn't there, then yeah, you could do arctan, you'd be done. But the squared throws everything off, right?
So the reason why we do it like this is just to split the x, split the problem in two. One side will be easy, and then we'll handle the rest
Exactly.
of the problem.
Exactly. We'll handle the rest.
And
we've got 10 minutes, so I'm going to give you all like 3 minutes to think about it. I'm going to step away for a moment. I'm going to see if I can come back. If anyone can figure out how to go about this one. I can tell you right now, it's not straightforward. All right. It's going to require something we've learned, but I want to see what you do. 3 minutes. Also, I'm going to pull the 2 out of it. Okay, just take the 2 back out. All right, and that way the integral is just this.
Is it integration by parts?
I'm going to come back in 3 minutes. Okay, everyone, so here's what I'm going to do. I'm going to launch a poll. Don't answer anything yet. Okay. The poll is going to be to see who thinks they have the way to go. If somebody has the right way to go on this, I'm going to give you 3 points on the next exam. So it's the first person who responds yes to this poll is going to get 3 points if they have the right way to do it. All right. If they don't, then I'm going to take away 10 points. I'm just kidding. I'm just kidding. I won't take away points. Ready? Here it comes. Okay, we have an answer. We have a couple people who think they know. Okay. I think that's good enough. Let's see who's who. I don't know how to look at the answers. Uh-oh. Oops, I have no idea how to tell who answered what. Shoot. How do I do this? I've never looked at who answered what. Okay, so who feels really good? I have 4 people who say they know it. So who feels really good about it? Four of you said you had an idea.
I don't feel good about it, but I have an idea.
Okay.
It's basically to use a mix of the constant quadratic with the no x term and the constant repeated linear integrals.
Okay. All right. I'm not going to say whether or not that is right or wrong. I'm going to give the other 3 an opportunity.
Can this be treated as the integral of u to the -2 and basically have 2 natural log of u plus c?
No, because your u is quadratic. So du would be 2x and you don't have 2x anywhere. That's what the blue integral up above it was. Right? The integral on the left
yeah.
here, because we had the 2x up there. We made that 2x appear. Okay, we have 2 others that are out there, but y'all need to answer quick.
I think we could use integration by parts here.
Okay, how about anyone else?
I also think it's integration by parts.
Okay. All right,
This
So-
is not, sorry.
anyone else?
I had a small little question.
Okay,
So can I ask if there is a 1 in front of the integral, like the second integral?
yeah.
Okay, so can we turn that 1 into x over x?
Outside the integral, no. Good question. Okay, so what was being suggested is, can we go and put like an x here and an x here? Or maybe you're even thinking a 2x, right? Because then if you pop that in here, then you've got du up top. The problem is you can't put anything other than a constant out in front of an integral.
Okay.
Good question. Good question. Okay. Unfortunately, nobody got it. It's okay. It's okay. You ready to see it?
Yes.
Tell me when you have the light bulb go off.
That's a trig sub.
That's a trick sub.
What?
We're going to realize that that whole quadratic being squared is actually the square root of something to the 4th.
Shit.
What?
That's a good answer. I like that. Do y'all agree?
Yeah.
Okay. Now I know that that problem can be done with trig sub. I can do x equals, I would do a tan theta here.
Yeah.
The dx would be secant squared theta d theta. And the square root part turns into secant theta. So this whole integral becomes 1 over the square root part to the 4th, and then dx, which is secant squared. And that just becomes 1 over secant squared. But 1 over secant is cosine. And now you power reduce, half angle, whatever, right? And it's doable now, ... It's probably not what you wanted to see, but now that you see it, right? I mean, it's in our, I'm not going to say it's in our wheelhouse, because usually that means it's in one of our strengths. We're not real good with trig sub yet because we just finished it, right? But now that I've shown it to you, I hope that you would agree that, yeah, you know, that's reasonable, and that's a problem that we should be able to handle. So, in summary of these last 2 that we did, If we see a linear over a quadratic, that quadratic on the bottom is irreducible. We're basically going to play this game where we let u be the denominator, the whole quadratic. We're going to look at its derivative. We're going to force the numerator to turn into that derivative. And then whatever's left over, that integral that's left on the outside, we're just going to have to figure out how to do it. Whether it be complete the square or trig sub or integration by parts, whatever it is going to be what it is. Okay? Now, where are we going next class? What we do is we put all this together. Those are the things that we need to know how to do before we can attack these problems. So these are the problems that we're going to be working on. This one, this one, this one, this one, this one, right? These problems. What is that for? 5 problems?
I have a question.
Uh-huh.
So right now, how many parts can we attempt for the homework at the partial fractions?
Not much. Actually, I don't even know if I would ask you to do anything out of this homework yet. Because we...
Then how can we practice these concepts?
Yeah. Well, how about I just write some problems down for you then? Right? I can
Yeah,
write
that can.
them down, and so you can practice them. I think the ones that are most difficult are these 6, 7, and 8. I think everything above that is a formula or just a basic U sub. So let me give you, like, for homework practice, some examples of like number 6, 7, and 8. So something you could do would be like integral. Let's just put a number up there just to make it worse for you. And then how about this? 4x squared minus, I'm just going to make this ugly. Is that all right? Just going to make it an ugly. You're going to get fractions, and there you go. So integrate that. Next one. Yeah, I don't want to be that bad. I don't want to be that bad. Okay, how about this? Hold on. I don't want to give you exactly the same problem. Oh. There. There's going to be lots of things to keep track of there with numbers, because you're going to have a lot of different issues come up, but see how it goes. I mean, that's good. I think that's a good practice for those 3 concepts there at the end. All right, Thursday we'll come back, right? And, you know, let me take a screenshot of this real quick because somebody's going to not remember the questions or something. Let me just save that. All right. Yeah, so we come back Thursday, and then when we talk about our exam, I know we're out of time. Our exam's not for a little bit, right? We still have a few classes. The 13th. Yeah, so we still got a little ways to go. Yeah. 2 weeks from today?
Yep.
All right, everyone, have a good one. if you're not sure what to do tonight, other than those problems, make sure you understand all of the trig sub stuff. Make sure you've gone through all those problems, you feel good about them. You can even go to the chapter review and look for problems that look like they're trig sub to you, or trig integrals out of the chapter review. It's good practice. All right, everyone, have a good one.
Thanks.
Do you have time after this?
I have a few minutes yet.
Okay.